Welcome back to the Deep Dive. If you're joining us, it means you need to quickly master something, well, something foundational, mission critical, and let's be honest, maybe a little intimidating.
Yeah, definitely foundational.
Today, we are undertaking a deep dive into the protocols that ensure every modern network, from the small office right up to the massive data center, doesn't immediately self-destruct.
That's a good way to put it, self-destruct.
We are diving into the spanning tree protocol STP and its absolutely crucial evolution, RSTP.
Right, STP and RSTP.
Our sources today, they're packed with mechanical detail, historical context, and really essential configuration nuggets.
And lots to unpack there.
The mission is sharp, it's clear. We're going to extract the core logic, trace the evolution, and really master the configuration features of these protocols.
Yep.
Why? Because redundancy, well, it isn't a luxury in modern networking, it's the expectation, right?
Absolutely. It's table stakes now.
But adding that second path, that failover link, it introduces this almost hidden existential threat that simply must be tamed.
It's exact.
We're exploring exactly how STP and RSTP save networks from that danger.
That analogy, saving the network from itself, it's perfect. Because the conflict is just... it's absolute. You must have redundant paths for high availability. You just have to.
No question.
But the standard operation of layer 2 switching, just how Ethernet works, dictates that those redundant paths, they create a disaster.
Right.
So STP-RSTP performs this necessary, highly critical balancing act. It preserves connectivity, making sure all devices can still reach each other while, simultaneously enforcing a stable, loop-free topology by selectively blocking those redundant links.
Okay.
We are going from this potential disaster zone to a structure of precision, and we really need to understand the fundamental logic that makes that possible.
Okay, let's unpack this immediately, because the elegance of the solution, you only truly appreciate it when you understand just how severe the problem is.
Definitely.
So what happens if you are, say, courageous network engineer, maybe a bit too courageous, and you add a redundant link between two switches, maybe late on a Friday,
Oh, boy.
and you forget, or maybe you don't know you need to, enable spanning tree? What is that nightmare scenario?
The short answer, and our sources really emphasize this, is sustained chaos. Just complete chaos that brings the entire switch domain to a grinding halt.
Not just slow, but halt.
Oh, yeah. When you introduce a physical loop and have absolutely no loop prevention mechanism, Ethernet frames will just cycle. They loop around the network indefinitely.
Indefinite. Like, how long?
I mean, the loop never ends. Not for an hour, not for a day, potentially forever, or, until a switch literally physically fails or someone figures it out and yanks the cable.
Wow. Okay. And crucially, this isn't just about wasting a little bit of bandwidth, is it?
Not at all. That's almost the least of your worries. This single failure mode, this loop, it triggers 3 interconnected catastrophic problems all at the same time.
3 things. Okay, let's start with the loudest one, the one everyone probably notices first.
Right.
The broadcast storm.
Precisely. That's the most obvious symptom. A broadcast storm gets kicked off by any frame that, by its very design, has to be flooded out of all interfaces in that VLAN, except, of course, the one it arrived on.
So things like ARP requests?
Yep. ARP requests, which are broadcasts, IP multicast traffic, and critically, even regular unicast frames, if the destination MES address isn't in the switch's table yet, those are called unknown unicasts.
Right, the switch doesn't know where it goes, so it floods it.
Exactly.
Yeah.
So the switch gets a broadcast frame on port A. Its basic logic says, flooded out ports B and C.
Okay.
That frame immediately hits the next switch in the loop, which does the same thing, floods it again.
And because of the loop.
Because of the loop, the original switch receives that same frame back, maybe on port B or port C this time.
And its own rules say.
Its basic layer 2 logic dictates it must flood it again. There's no intelligence saying, I've seen this before.
So they just multiply.
Exponentially. Within milliseconds, the frames are just replicating like crazy, consuming all the available bandwidth. The links get completely saturated.
Which means no legitimate traffic gets through.
Correct. It crowds out all the good user frames. But more subtly, and maybe even more agonizingly for the end user, think about every connected PC, every server, every IoT device.
They see all this traffic.
They have to process this excessive, unrelenting stream of looping broadcast frames. Their CPUs just get hammered trying to figure out, is this frame for me? No. Is this frame for me? No. Over and over.
Leading to
complete client device performance degradation. Everything just grinds to a halt because the endpoints are too busy dealing with the storm.
Okay, so that's disaster number 1. a network where nothing can get through and all the devices are choking. But you said that's only part of the story. There's a second, maybe more dangerous problem.
Yes. MC table instability. This one is the subtler killer.
How does that work? Normally, switches learn MSE addresses, right?
They do. A switch learns a host's MSE address and associates it with a specific port. Host A is out port 1, nice and stable.
But with loops,
With looping frames, the same frame from the same host keeps arriving on different ports because of that cycle.
oh, I see.
And this forces the switch's MSE address tables to continually update or flip-flop.
Let's use that Bob example from the sources. It was pretty clear.
Yeah, okay. So Bob is connected to switch 3's 501 port. SW3 learns, okay, Bob's MC is on now below 101. Solid entry.
Then Bob sends a broadcast like an ARP.
Right, and it loops. It goes from SW3, maybe over to SW2, then across to SW1, and eventually, because of that redundant link we added...
It comes back into SW3, but on a different port.
Exactly. Let's say it loops back into SW3's redundant port, G01.
What does SW3 do then?
Well, the switch learning process is absolute. It sees Bob's frame arrive on G01 and immediately thinks, wait, I just saw Bob's frame on G01? That must be where Bob is now.
So it updates the table.
It overwrites the entry. It points Bob's MSC address to G01 now.
And the consequence...
Now, if another host, say Larry, tries to send traffic to Bob, SW3 looks up Bob's MC, sees G01, and incorrectly forwards Larry's frame out G01, sending it off into the looping segment towards SW1.
Instead of delivering it locally to Bob on FAS03.
Precisely. The traffic never reaches Bob. And then, maybe a few seconds or minutes later, another broadcast from Bob might arrive on the correct port, FAS033.
And it flips back.
And it flips back again. The table is completely unstable because the entries are constantly toggling between the ports on that redundant path. Reliable delivery becomes impossible.
Okay, that sounds really bad. Broadcast storms, unstable MFE tables. What's the third leg of this disaster stool?
That leads directly to the third issue, multiple frame transmitters.
So getting the same data more than once.
Exactly. Even if the network hasn't, entirely melted down yet from the storm or the MSC flapping, let's say Bob sends a unicast frame to Larry, but the switches haven't learned Larry's address yet.
So they flood it, like an unknown unicast.
Right. They flood it. But because of the loop, Larry ends up receiving multiple, identical, unnecessary copies of that single frame Bob sent.
And that causes problems.
Well, it's not just inefficient. It can seriously confuse higher layer protocols like TCP or cause applications running on Larry's machine to fail because they just aren't designed to handle duplicate data streams arriving like that.
Okay, the need is undeniable. Broadcast storms, MSE instability, multiple frames. It's a complete meltdown.
Total meltdown.
So STP has to break that loop. It does this by forcing some of those interfaces into a blocking state.
That's the core idea. Simple in concept, really. Force some interfaces into a blocking state to break the physical loop into a logical tree structure.
We sacrifice the use of an available link. That's the minor negative side effect you mentioned.
Exactly. You don't get to use that extra bandwidth, but you gain total network stability.
And that stability is absolutely the cost of entry for any serious network design.
It is the foundation. Without it, nothing else works reliably.
Okay, so now we pivot from the chaos to the precision. How does the spanning tree algorithm, the STA, actually execute this? How does it build this stable, loop-free topology?
Right. The STA, it's essentially the sophisticated negotiation process that happens between the switches.
The negotiation.
Yeah, they talk to each other using special messages, BPDUs, to figure out the best loop-free path. It determines which interfaces get the green light, the forwarding state, and which ones have to sit idle in the blocking state.
And the goal is to impose a tree structure, like mathematically.
Exactly. A hierarchy with a single root, ensuring there's only ever one active path between any 2 points in the layer 2 domain at any given time.
And the protocol relies on, 3 core criteria. For a port to be allowed to forward traffic.
Yes, 3 fundamental rules or steps in the process. Step 1, electing the root switch.
The king of the castle.
Pretty much. This switch becomes the unwavering reference point, the center of this logical tree. And by definition, all working ports on the root switch itself must be placed into a forwarding state. They're the starting point for all paths.
Okay, makes sense. One root, all its ports are active. Step 2.
Step 2, every other switch, every non-root switch, must choose its root port, RP.
Root port, what's that?
The RP is the single port on that non-root switch that provides the absolute least cost path back towards the root switch that was just elected.
Least cost. We'll have to define cost later, but okay.
Yep.
One best path back to the root.
Just one root port per non-root switch. That's crucial.
Got it. And step 3.
Step 3. On every individual LAN segment, so basically every link connecting two switches or a switch and a hub, if you still have those.
Hopefully not.
Hopefully not. On each link the switches connected to it must elect a single designated port, DP.
Designated port. So one port on that link gets picked?
Right. The designated port belongs to the designated switch for that segment. And usually the designated switch is the one that has the lowest path cost to the root.
So it's considered the switch responsible for forwarding traffic onto that segment towards the root or away from it?
Exactly. It's the most efficient path from that specific link towards the root.
Okay, root switch election, root port selection on non-roots, designated port selection on each link. That's the framework.
That's the logical framework. And this entire structure, this whole negotiation, is built upon something called the bridge ID, or BD.
The BD. Okay, let's delve into those election mechanics now, because it sounds like understanding the BID is how you understand control over your topology.
Absolutely. The B by D is everything when it comes to determining the root and influencing paths. It's an 8-byte value, and it has to be unique for every single switch in the network.
8 bytes. How is it structured?
It's a composite value. The first 2 bytes are the priority field. This is the important one for configuration.
Okay, priority.
The next 6 bytes form the system ID. And this is typically derived directly from the switch's universal burned-in MAC address. Usually one of the ASCII addresses assigned to the switch.
So priority plus MC address equals BID.
Basically, yes. Although technically the system ID might include a VLAN ID component in some variants, but the core is priority plus unique MC identifier.
And the golden rule for the election, you said it earlier.
Simple. The switch with the numerically lowest bridge ID wins the root election. Lower is better.
Lowest overall 8-byte value.
Yes, but it checks the priority field first. That's the most significant part.
Okay, and the priority field, that's where engineers can step in.
Exactly. By default, Cisco switches often use a priority value like 32,768 plus the VLAN ID, so maybe 32,769 for VLAN 1. It's a high number.
But you can change it.
Yes, you can manually configure a much lower priority value, like 4096 or 8192 or even 0, though that's generally not recommended.
So if one switch has a priority of 4096 and all the others are at the default, say 32,769.
The switch with 4096 wins immediately, hands down. The MAC address part of the BID becomes irrelevant at that point because the priority is so much lower.
So that's how you guarantee your big, powerful core switch becomes the root. You just give it the lowest priority.
Precisely. That's how engineers influence the outcome and make the topology predictable. By lowering the priority, you ensure your chosen, most capable switch becomes the root.
But what if you don't configure it? What if all switches are just left at their default priority? Which I imagine happens a lot in, unmanaged or quickly set up networks.
It happens all the time. In that case, if the priorities tie, then the MAC address portion of the BID serves as the ultimate tiebreaker.
So the switch with the lowest MAC address wins.
The switch with the numerically lowest MAC address wins the entire election. Since MAC addresses are unique globally, this guarantees a winner.
But it's basically a lottery at that point, right? Some random switch, maybe an older, slower one, could end up being the root just because it has a lower MS.
Exactly. It's unpredictable unless you manually intervene with the priority setting. You might end up with a suboptimal route, leading to inefficient paths.
Okay, so the election process itself, how does that actually happen? Do they vote?
Haha, not quite voting. It's more like a dynamic campaign. Initially, every switch thinks it is the root.
Bit arrogant.
Well, it doesn't know any better yet. So each switch starts sending out special messages called Hello BPDUs. BPDU stands for Bridge Protocol Data Unit.
Hello messages. Okay.
In these hellos, they announce their own BID and claim, I am the root.
Okay.
Now, if a switch receives a Hello BPDU from a neighbor, and that hello contains a BID that is better, meaning numerically lower than its own BDD.
It realizes it's not the best candidate.
Exactly. It recognizes that incoming message as a superior hello. At that point, it stops claiming to be the root itself.
And does what?
It stops sending its own hellos claiming root status and instead starts forwarding the superior hello it received. It essentially drops out of the race and starts campaigning for the better candidate it just heard about.
I see. So the better beads propagate through the network.
Right. This process continues, with switches constantly comparing the beads they hear, until eventually everyone agrees on which switch has the absolute lowest BD. Only that one true root switch continues generating hellos claiming to be the root. Everyone else just forwards those hellos.
Consensus is reached.
Consensus is reached.
And those BPDUs, those hello messages, they must carry more than just the BID, right? They're the lifeblood of this whole thing.
Oh, yeah. That Hello BPDU is extremely dense with information. It's carrying everything needed to calculate the topology and maintain it.
What's in there?
4 critical pieces of information. First, obviously, the root bridge ID, the BD of the switch the sender believes is the current root.
Okay.
Second, the sender's bridge ID, the BD of the switch that actually sent this specific hello message.
So who the root is and who's telling me.
Correct. Third, the sender's root cost. This is the sending switch's calculated cost to reach the root switch it just named.
The cost we mentioned earlier,
Yeah.
how far away they think the root is.
Exactly. And finally, the STP timer values. Things like how often hellos are sent, how long to wait before declaring a neighbor dead, etc. These timers are actually dictated by the root switch itself and propagated outwards in the hellos.
Okay, so root BD, sender's cost to root, and timers. Lots of info.
Yep. And non-root switches use all this information, particularly the sender's root cost, to figure out their own best path back to the root to choose their root port.
How does that calculation work? Is it just adding things up?
It's fundamentally additive, yes. When a non-root switch receives a hello BPDU on one of its ports, it takes the advertised root cost from that hello, that's the sender's root cost value we just talked about.
Okay, the cost the neighbor claims it takes them to get to the root.
Right. And then the switch adds its own local interface's RSTP cost to that advertised value. This local cost is based on the speed of the link the hello came in on.
So neighbor's cost plus my link's cost, total path cost for this path.
Exactly. The switch does this calculation for every port it receives a hello on. The port that results in the lowest total calculated cost is chosen as the root port. That's the best path back to the root from this switch's perspective.
Let's walk through that calculation example from the source material. It involved 3 switches, SW1, SW2, SW3, with SW1 being the root.
Okay, good idea. So SW1 is the root. Its cost to itself is 0. SW3 needs to choose its root port. It has 2 potential paths, a direct link to SW1 and a link that goes through SW2 first.
Okay, path A, the direct link from SW3 to SW1. SW1 sends a hello directly to SW3. What cost does SW1 advertise?
SW1 advertises a root cost of 0 because it is the root.
Right. Now let's say the link between SW1 and SW3 is a 1 gigabit Ethernet link. What's the typical cost for that?
Depends on the standard, but let's use the older, simpler short cost for now. A 1 Kbps link has a cost of 4.
Okay, so SW3 calculates 0, advertised cost from SW1, plus 4, SW3's local GO1 interface cost, a total path cost of 4 for path A.
Correct. Cost of 4 via the direct link. Now path B through SW2.
Right. SW2 first needs to figure out its cost to SW1. Let's say it also has a direct 1 gig link to SW1.
Okay, so SW2 calculates its cost as 0 plus 4 equals 4. SW2 knows its root cost is 4.
Now, SW2 sends hellos out its other ports, including the one connected to SW3. What cost does SW2 advertise in those hellos?
SW2 advertises its calculated root cost, which is 4.
Okay. Now, SW3 receives this hello from SW2 on, say, its GOW2 port. Let's assume the SW2-SW3 link is also 1 Gbp, so cost 4.
Right, so SW3 calculates the cost for path B4, advertised cost received from SW2, plus 4 SW3's local GO2 interface cost, a total path cost of 8.
So path A costs 4, path B costs 8.
4 beats 8.
Clearly.
Therefore, SW3 chooses the direct link to SW1, its GO1 interface, as its root port. That port gets the green light to move towards the forwarding state. Simple arithmetic dictates the primary topology.
But what happens if the costs tie? Say both paths somehow worked out to a cost of 4.
Excellent question. STP needs absolute determinism. It can't have ambiguity. So, if the total root path costs are equal, the switches move to a strict series of tiebreakers. There are 3 main ones applied in order.
Okay, tiebreaker number 1.
First, they choose the path that leads towards the switch with the lowest neighbor bridge ID.
So even if the cost is the same, it prefers the path going to the upstream neighbor switch that has the better, lower overall BD.
Exactly. The logic is that the switch with the lower BID is generally considered more authoritative or closer to the root, so it's a better upstream choice if costs are equal.
Makes sense. What if the neighbor beads also tie? Like if SW3 had 2 parallel links going to the same neighbor SW2 and both calculated the same cost.
Good scenario. If the neighbor beads tie, which typically only happens with parallel links to the same switch, they move to the second tiebreaker. Lowest neighbor port priority.
Port priority, that's different from the switch priority.
Yes. This is a value you can configure on the neighbor's interface itself. By default, it's usually 108. But an administrator can lower the priority on one of the parallel links, say, set it to 64.
Ah, so the neighbor switch is advertising which of its own ports it prefers you use to reach it.
Kind of. It allows the network engineer to administratively influence which specific parallel link is favored when costs and neighbor beads are identical. It gives you fine-grained control.
Okay, what if the costs tie? The neighbor beads tie and the neighbor port priorities tie. Is that even possible?
It is, especially if you haven't configured port priorities. So the final ultimate tiebreaker is the lowest neighbor internal port number.
Just the physical port number, like FASO1 versus FASO2.
Exactly that. The switch will prefer the path coming from the neighbor's port with the lower physical number. The example, FASO1 beats FASO2, G01 beats G02. It's the last resort to guarantee a definitive choice is always made, even in a perfectly symmetrical scenario.
Wow, okay. Cost, then neighbor BD, then neighbor port priority, then neighbor port number. Very deterministic.
Has to be. Any ambiguity could lead to loops.
So once all the non-root switches have figured out their root ports using this cost and tiebreaker logic, what's the next step? We still need the designated ports, right?
Correct. The root ports are established. Now we need to figure out the designated port and DP on each individual link segment. This is the third rule for deciding which ports forward.
And this is a local contest happening on each link independently.
Yes, link by link. The switches connected to a particular segment exchange hellos and compare their own root costs.
Okay.
The switch that is advertising the lowest root cost onto that segment wins the election for that specific segment. Its port connected to that segment becomes the designated port.
Back to our SW2, SW3 example link. SW2 is advertising a root cost of 4 onto that link. SW3, before choosing its RP, would have calculated its cost through SW2 as 8.
Right, so on that segment, SW2 advertises cost 4 and SW3 advertises cost 8, or potentially its direct cost of 4 if it advertised that way. It depends on the exact timing. But let's stick to the scenario where SW2 is better.
Okay, let's say SW2 advertises 4, SW3 advertises 8.
SW2 clearly wins on that segment because 4 is lower than 8. So SW2's port on the link connecting to SW3 becomes the designated port for that segment.
And SW3's port on that same link, since SW3 already chose its other port, ROYA1, as its root port.
SW3's port just SW2 on the link to SW2 becomes neither a root port nor a designated port. Therefore, it must be put into the blocking state. That's how the loop is broken.
Got it. What if the root costs advertised onto the segment tied? Say both SW2 and SW3 advertised a root cost of 4 onto that link.
Another tiebreaker needed. If the root costs advertised onto the segment tie, the switch with the lower bridge ID wins the election for that segment.
Ah, so the switch that's generally better or closer to the root gets to be the designated forwarder for that link.
Exactly. Again, ensuring determinism.
So let's summarize the forwarding state then. Who forwards and who blocks?
Simple summary. All root ports forward, all designated ports forward. Every other active interface on a switch that's physically up but isn't in RP or DP must be placed in the blocking state.
Blocking means no user data goes through, right? But it still listens to BPDUs.
Correct. It doesn't forward user frames, doesn't learn MAC addresses, but it absolutely still processes incoming BPDUs, so it can react if the topology needs to change.
Okay. What about ports connected to end devices? Like my laptop or a server or a printer. They don't run spanning tree.
Right. Good point. Ports connecting to devices that do not run STP, we call them edge ports, sometimes have a simpler life.
Well, so?
Since those endpoint devices never send out BPDUs, the switch port connected to them never hears any challenge. It sends out hellos, here's nothing back.
So it just assumes it wins.
It effectively wins the designated port election for that segment by default. There's no competition. So ports connected to endpoints typically become designated ports and move pretty quickly into the forwarding state.
Okay, that makes sense. Now let's talk about control again. We know we can set the priority to choose the route, but path control seems really important too. How do engineers actively influence which links become route ports or designated ports?
Right. You don't want to leave paths entirely up to default costs or MAC addresses if you have specific design goals. The two main levers, as we said, are the bridge ID, primarily the priority part, and the port costs.
We covered setting the BID priority lower, like 4096, 80192, to pick the route and maybe a backup route. How does manipulating the port costs work?
You can manually configure the STP cost value assigned to a specific interface on a switch. By default, the cost is derived from the link speed, but you can override it.
So if I have two links to the root, maybe one is 1 GDP's, default cost 4, the other's older, say 100 MELIP's, default cost 19.
The 1 GBP's link will naturally be chosen as the root port because cost 4 is much better than cost 19.
But what if I wanted, for some odd reason, to force traffic over the 100 BBP's link?
You could manually set the cost on the 1 GBP's interface to something higher than 19, say set its cost to 20.
Yeah.
Then the 100 mini-P's link, cost 19, would suddenly look like the better path, and it would become the root port.
So lowering the cost makes a path more attractive, raising it makes it less attractive.
Exactly. It directly influences the root cost calculation we walked through earlier.
Now, about those default costs, you mentioned 1 GBP's is 4, 100 MBP's is 19. Are those universal?
Well, those are the values from the original IE 802.1d standard from 1998, often called the short method or 32-bit path cost. They worked okay for a while.
Costs were 10 MBP's equals 100, 100 BBP's equals 19, 1 GBP's equals 4, 10 GBP's equals 2.
Right. But you see the problem.
Yeah, 10 gig has a cost of 2. What about 40 gig? Or 100 gig?
Exactly. The cost difference between 1 gig cost 4 and 10 gig cost 2 is tiny. And speeds beyond 10 gig would also likely end up with a cost of 1 or 2. The standard ran out of granularity. It couldn't properly differentiate between faster modern links.
They had to update it.
They did. The IU revised it in 2004 with what's now called the long method or 64-bit pass cost. This uses much larger values.
Like what?
For example, under the long method, 10 MBP's is 2 mils in mol, 100 MBP's is 200,000, 1 GBP's is 20,000, 10 GBP's is 2,000, 100 GBP's is 200.
Wow, much bigger numbers, much more room to differentiate.
Exactly. It provides dramatically better granularity, allowing the protocol to accurately compare and prioritize today's high-speed links much more effectively. Most modern switches use the long method by default now.
Okay, that's important. Short versus long cost methods. But there was another critical detail, a trap you mentioned, about how Cisco switches determine that default cost.
Yes, this is a huge one. A real potential gotcha for network designers, and it's highlighted clearly in the source material we looked at. Cisco switches determine the default STP cost based on the actual operating speed of the link at that moment.
Not its maximum rated capacity.
Correct. Not its potential speed, but its current speed.
So if I have a port that's capable of gigabit Ethernet, maybe it's a 10-100, 1000 port,
Yep.
but maybe due to a bad cable or a configuration mismatch or auto negotiation failing, it only connects at 10 MBP's.
Then its default STP cost will be calculated as if it were only a 10 LEP link. Using the long cost, that would be $2 million.
Even though it could run at 1 GBP's, costs 20,000.
Yes. Even though the hardware is capable of much more, if it negotiates down to 10 MELIPs, STP sees it as a 10 MELIPs link and assigns the corresponding high cost.
That could completely mess up your intended paths. That slow link might suddenly look incredibly expensive, forcing traffic onto a path you didn't want.
Absolutely. It can lead to really suboptimal routing if you're not watching your actual link operating speeds. You might think you have a high-speed path, but STP sees it differently because of a negotiation issue.
That is a crucial detail. Always check the operational speed.
Always. Okay, so we built this stable state. We have a root ports, designated ports, costs are calculated, loops are blocked. This is the network's normal happy mode.
Right. Steady state.
But this system, particularly the original 802.1d STP, was developed back in the early 90s. And its primary weakness, its Achilles heel, really emerged when networks started demanding faster recovery, instant failover.
Ah, okay. So it's stable, but what happens when something breaks?
Exactly. We need to talk about traditional STKey's crippling flaw. It's incredibly slow convergence.
This is where it gets, as you said, really interesting and historically pretty frustrating for network folks.
Oh, incredibly frustrating. Traditional STP, the 802.1d standard, it was designed for resiliency, yes, but absolutely not for speed.
And back then, maybe waiting a minute was acceptable.
Maybe in the very early days. But as applications became more critical, that speed, or rather the lack of it, became an existential crisis for network engineers. When a primary link failed, network services were often down for nearly a minute before the backup path took over.
A minute. That's ages in application terms.
It's an eternity. So let's look at why it was so slow. In steady state, we know the root switch sends out a hello every 2 seconds by default. Non-root switches just forward these.
Okay.
But when a topology change occurs, like a link failing or a switch going down, and a non-root switch maybe loses connection to its upstream neighbor or the root itself, The recovery process is bound by these strict, lengthy timers.
Timers designed to prevent temporary loops during the transition.
That was the primary fear, yes. They were very conservative to ensure stability above all else.
So what are these timers? You mentioned three key ones.
Right. The hello timer, we know, default 2 seconds. That's just the heartbeat.
Okay.
Then we hit the big one, the maxage timer. Default is 20 seconds.
20 seconds. What's that for?
This is the crucial, frustrating waiting period. If a non-root switch stops hearing hellos on its root port, it doesn't react immediately. It waits for maxage 20 seconds before it even considers that its path to the root might be gone and that a topology change might be needed.
It just sits there for 20 seconds, potentially knowing the link is down.
Well, it doesn't assume the root is gone just because one hello is missed. It waits 10 hello intervals, 10 by 2s equals 20s, to be absolutely sure the path is invalid before aging out the old information.
Okay, 20 seconds of waiting. What's the third timer?
The third one is the forward delay timer. Default is 15 seconds.
15 seconds. And that applies.
How?
This delay dictates the time a port must spend in each of the two special interim states, listening and learning when it's transitioning from the blocking state towards the forwarding state. Two interim states, listening and learning. Why?
Again, to prevent temporary loops. They figured the network needed time to stabilize and for MC address tables to be updated correctly before a previously blocked port was allowed to actually start forwarding traffic. Each state lasts for the forward delay time.
So 15 seconds in listening, then 15 seconds in learning. That's 30 seconds just for the transition.
Exactly. And these interim steps were deemed absolutely necessary back then.
Okay, so if we add these up, maxage wait plus the two transition states.
You get the infamous 50-second convergence delay for traditional STP. 20's maxage plus 15's listening plus 15's learning equal 50 seconds.
50 seconds. Wow. Let's trace how that plays out. Say an alternate path needs to activate because the primary root port link failed.
Okay, let's use our SW1 root and SW3 example again.
Right.
Assume the direct link between SW1 and SW3 fails. But maybe it's not a clean physical down, maybe it's a software issue or something where SW3 just stops receiving hellos from SW1 on its root port, GR01.
So the link might still show up, but the hellos aren't coming through.
Right. SW3 has to wait. It waits the full 20 seconds for the max edge timer to expire before it can even officially declare that its old root path information is invalid and start considering its alternate path through SW2 on GO2.
Okay, after that agonizing 20-second wait.
The formerly blocking alternate port, G02, begins its transition. It first moves into the listening state,
It's this for.
the full 15 seconds of the forward delay timer. During this time, the port is not forwarding any user frames, but the switch uses this time to start removing old, potentially stale MS table entries that it learned via the now dead path.
Why remove them?
Because those stale entries pointing out the old failed port could absolutely cause a temporary loop if this new port started forwarding frames immediately. So clean up first.
Okay, 15 seconds of listening and cleaning, then what?
Then it moves into the learning state for another 15 seconds.
Still not forwarding user traffic.
Still no user frames forwarded. But in the learning state, the switch begins to learn new MAC addresses based on frames arriving on this interface, GIO22. It starts rebuilding its MSC table based on the new topology.
So 15 seconds listening, 15 seconds learning.
Only after that entire 50-second process does the port, GIO22, finally transition into the forwarding state and start passing user traffic over the backup path.
50 seconds. I remember troubleshooting systems back in the day where that literally meant phones dropping calls, critical applications timing out. It was brutal.
Absolutely brutal. That inability to recover quickly, that 50-second outage, became the absolute death knell for traditional STP in any network that cared about availability. It directly spurred the need for a rapid solution.
Which is exactly what we got, thankfully. RSTP, Rapid Spanning Tree Protocol.
Thank goodness for RSTP, standardized as IEEE 802.1W. The rapid in RSTP directly addresses this massive time sink. It drops that convergence time dramatically.
From 50 seconds down?
Often down to just a few seconds, maybe 6 seconds in some scenarios, based on missed hellos, or even less than a second in the best case failover scenarios. It's a night and day difference.
Okay, so how does RSTP achieve this magic? Does it throw out all the old rules?
No, that's the beauty of it. RSTP retains the foundational rules. It uses the same methods for electing the root switch, choosing the root port based on cost, and electing designated ports based on cost and BID.
So the final topology looks the same?
The final stable topology is calculated using the same logic, yes. And crucially, RSTP is fully backward compatible. An RSTP switch can operate perfectly fine with older STP switches in the same network, although you lose some of the speed benefits on segments connected to STP devices.
Okay, same basic structure. So what's the key difference? How does it get so fast?
The core difference is the shift away from relying solely on those slow timers, like maxage, listening, learning for recovery. Instead, RSTP uses more active message-based coordination between switches.
More talking, less waiting?
Exactly. Peer-to-peer messaging instead of just passively waiting for timers to expire. Maxage itself is also significantly shortened. It's now typically just 3 times the hello interval, so 3 by 2 is 6 seconds instead of 20
And
seconds.
6 seconds is much better than 20.
Much better. And another fundamental change, unlike STP, where only the root switch originated the hello BPDUs.
Right, and everyone else just forwarded them.
In RSTP, each RSTP-capable switch independently generates and sends its own hello BPDUs every 2 seconds. By default. They don't just relay them from the root.
Why does that help?
It allows for much faster detection of neighbor failures. If a switch misses 3 consecutive hellos directly from its neighbor, so about 6 seconds, it immediately assumes that neighbor is down and can start the convergence process much faster without waiting for information to propagate all the way from the root.
Okay, faster failure detection via shorter maxage. What else contributes to the speed?
2 really big innovations are key. First, the definition of more explicit port roles that predefine backup paths. And second, the use of a rapid proposal agreement, PA, handshake mechanism between switches.
Proposal agreement, what's that?
This PA handshake is the magic that essentially cuts the cord on those 30 seconds of listening and learning states for transitions on point-to-point links between RSTP switches.
How does it work?
When an RSTP switch brings up a link to another RSTP switch, one of them, usually the one that thinks it should be the DP, sends a proposal message. It's basically saying, hey, I propose that my port should be the designated port for this link, and I want to move it to forwarding immediately.
Okay. What does the other switch do?
The receiving switch evaluates the proposal. If it agrees, it calculates this path is indeed its best path to the root, making its port the root port. It prepares itself. It synchronizes its other ports, first essentially blocking them temporarily to ensure no loops can form during this transition.
A quick temporary block.
Yes, a very quick synchronization step. Once it's sure no loop will be created, it sends back an agreement message to the proposing switch.
And then?
As soon as the proposing switch receives that agreement, both switches can immediately transition their respective ports on that link, the DP and the RP, directly into the forwarding state.
Skipping listening and learning entirely.
Skipping the full 30 seconds. This handshake ensures both ends are ready and synchronized, guaranteeing no temporary loops are created, which was the whole reason for the slow timers in STP.
That sounds much, much faster, like almost instant connection establishment.
On point-to-point links between RSTP switches, yes, it's very fast. This PA mechanism is fundamental to RSTP's speed.
Okay, and you also mentioned new port roles.
Yes. This focus on rapid recovery leads RSTP to define more specialized port roles, particularly for handling failover scenarios explicitly. The most critical new one is the alternate port, ALT.
Alternate port, what does that signify?
RSTP explicitly identifies and names the port on a switch that offers the second best path back to the root switch. It's the runner-up to the root port.
So the switch knows this is my best path, RP, and this other port is my backup path, ALT.
Precisely. That alternate port is sitting there in a blocking or technically discarding state, but it's fully negotiated and ready to take over instantly if needed.
And how does that help with failover speed?
When the primary root port fails, and importantly, if the physical link goes down, RSTP detects that failure almost instantly, much faster than waiting for missed hellos.
Okay, instant detection on link down.
Right. When that root port fails, RSTP triggers a rapid failover. The designated alternate port immediately assumes the root port role.
And transitions to?
It transitions instantly to the forwarding state.
Again, skipping listening and learning.
Yes. Because RSTP knows this was the pre-calculated safe backup path, and its synchronization mechanisms, like flushing relevant MASI table entries quickly based on the topology change notification, handle the loop prevention. There's no need for those long waiting states.
So, if the primary link fails physically, the backup alternate port can take over almost immediately.
Yes. This can achieve sub-second convergence in many cases. It's a massive improvement over STP's 50 seconds.
Huge difference. Now, RSTP also included another role, the backup port. You mentioned this one is mostly academic now.
Yeah, the backup port role exists in the standard, but it's designed as a backup for a designated port. It really only comes into play in scenarios involving non-point-to-point links, specifically shared media environments.
Like connecting switches to an old Ethernet hub.
Exactly. If you had multiple switch ports connected to the same hub, one would be the DP and another might become a backup port, ready to take over as DP if the primary DP failed.
But nobody uses hubs anymore in switch networks.
Pretty much. Modern switch networks almost exclusively use point-to-point links between switches, or switches and endpoints. In these environments, you'll really only encounter root ports, designated ports, and alternate ports. So the backup port role is mostly just a historical footnote for understanding the full standard.
Okay, good clarification. Let's quickly look at the port states, too. RSTP streamlines these compared to STP, right?
It does. It simplifies them. RSTP still uses the learning and forwarding states, which functions similarly to how they did in STP, though, as we saw, learning is often bypassed now, thanks to the PA mechanism.
What about blocking?
The key consolidation is the discarding state in RSTP. This single state effectively replaces both the old STP blocking state, where a port is actively up but blocking to prevent a loop, and the old disabled state, where a port is administratively shut down or physically down. If a port isn't learning or forwarding, it's discarding.
Simpler. Discarding, learning, forwarding. What about the listening state?
Gone. RSTP completely eliminates the listening state.
Right.
Because the rapid convergence provided by things like the PA handshake and the immediate failover using alternate ports makes that 15-second waiting period completely unnecessary for loop prevention on modern links. It was just dead time.
Makes sense. Faster mechanisms mean you don't need the cautious waiting period.
Exactly.
Okay, so RSTP dramatically solves the primary historical issue, the slow convergence. But even with rapid convergence, there are still situations where we need more tactical tools, right? Optional features to really optimize the topology, harden the network edges, and maybe add some security.
Absolutely. The core RSTP protocol is great, but for building truly robust and secure production networks, network engineers rely heavily on a suite of optional but often essential spanning tree features.
Let's dive into those practical tools now. What's first?
Well, first, let's talk about the feature that provides the absolute fastest path to link availability, arguably even faster than RSTP failover, Ether channel.
Ether channel or port channeling. That's where you bundle multiple physical links together.
Exactly. You can bundle up to 8 parallel physical links, like 8 individual Ethernet cables between the same 2 switches, and treat them as one single logical link called a port channel or Ether channel.
How does STP see that bundle?
From STP's perspective, the entire bundle, all 8 physical links, operates as a single logical interface. It gets assigned a single STP cost, usually based on the aggregate bandwidth, and it participates in STP as just one port.
What's the advantage for availability?
It's enormous. Imagine you have an 8-link Ether channel carrying critical traffic. If one or even several of those physical cables within the bundle fails or gets unplugged,
STP doesn't even notice.
STP convergence is completely irrelevant. As long as at least one physical link within that bundle remains active, the Ether channel interface stays up. Traffic is simply automatically redistributed by the switches across the remaining active links in the bundle.
So failover is essentially instant because there's no protocol convergence needed at all.
Exactly. It leads to near instant availability as long as the entire bundle doesn't fail. This is why Ether channel is the absolute gold standard for building robust, high availability connections between core switches or between switches and critical servers.
Okay, Ether channel avoids convergence altogether. What about features that work with STP-RSTP? Let's talk about the network edge connecting user devices.
Right. The edge is critical, and the essential feature there is port fast.
Port fast. We touched on this briefly. It speeds up connection for endpoints.
Yes. Port fast is specifically designed for switch ports that connect directly to a single endpoint device, a PC, a server, an IP phone, a printer, something that definitely won't be another switch creating a loop.
And what does it do?
It basically tells the switch, trust me, there's no loop risk on this port. When you enable port fast on an interface, as soon as that physical link comes up, like when a user plugs in their laptop,
The switch doesn't wait.
it immediately moves that port into the designated port role and straight into the forwarding state. It completely bypasses the usual 30 seconds or even the faster RSTP negotiation of listening and learning synchronization.
So the device gets network connectivity instantly.
Instantly, which is huge for user experience. Think about booting up a PC or an IP phone. You don't want to wait 30 seconds just for the switch port to become active. Port fast eliminates that delay.
That speed is great, but you said it comes with a huge inherent danger. What was that again?
A critical danger.
Yeah.
Because a port fast enabled port achieves its speed by essentially ignoring the normal STP-RSTP negotiation process and ignoring incoming BPDUs initially if you make a mistake.
Like accidentally plugging another switch into that port fast port.
Exactly. If you accidentally connect another switch, hub, or any BPDU generating device to a port fast enabled port, that rogue device will start forwarding traffic immediately without going through the proper STP election and blocking process.
Yeah.
An unmitigated instantaneous forwarding loop. The result is an immediate broadcast storm and likely network meltdown. Port fast assumes safety, and if you violate that assumption, the consequences are severe.
Okay, so that's a common mistake engineers could make. How do you protect against it? You can't just rely on people never making mistakes.
You absolutely cannot, which is why engineers must pair port fast with another crucial feature, BPDU guard.
BPDU guard. This sounds like a security feature.
It is. It acts as the safety net for port fast. BPDU guard operates on a very simple principle. A properly configured port fast port connected only to an endpoint should never, ever receive a BPDU.
Because endpoints don't send BPDUs.
Correct. So if a port with BPDU guard enabled does receive any BPDU,
It knows something is wrong. A switch has been plugged in.
Exactly. BPDU guard detects that rogue switch connection instantly based on the incoming BPDU, and its reaction is swift and severe.
What does it do?
It immediately disables the port. It puts the port in a special error-disabled state. The port is effectively shut down, killed instantly.
Wow. So it sacrifices connectivity on that port to save the rest of the network.
Absolutely. BPDU guard prioritizes overall network stability above all else. It assumes any BPDU on a port fast port is a dangerous configuration error and takes the most aggressive action possible, shutting the port down to guarantee the network remains stable and loop-free.
Okay, the nuclear option. Is there a less aggressive way to handle that situation?
There is, and that brings us to BPDU filter. Now, BPDU filter is slightly confusing, as the sources noted, because it actually have two very distinct modes of operation, depending on how it's configured.
Two uses. Okay, what's the first use? Maybe the one related to port fast.
The first use is configured globally, often tied to port fast enablement globally. In this mode, it acts as a less aggressive alternative to BPDU guard if an unexpected BPDU arrives on a port fast enabled port.
Instead of shutting the port down.
BPDU filter reacts by simply disabling the port fast feature on that specific port. It doesn't shut the port down. It essentially says, whoa, I received a BPDU here, so this clearly isn't just an endpoint anymore. I'm turning off the port fast shortcut.
And then the port does what?
The port then reverts back to operating under the normal, slower STP-RSTP rules. It will start processing BPDUs, go through the listening, learning, or RSTP's synchronization states, and negotiate its role, likely becoming blocked, to prevent the loop.
So it manages the risk by falling back to standard STP behavior rather than just killing the connection like BPDU guard.
Exactly. It prevents the loop, but attempts to maintain connectivity, albeit with the standard STP convergence delay kicking in. It's a trade-off between immediate shutdown, BPD guard, and managed fallback, BPDU filter global mode.
Okay, that makes sense. What's the second more radical use of BPDU filter?
The second use is configured directly on a specific interface using an interface subcommand. When configured this way, BPDU filter does something much more drastic. It completely filters, discards, all outgoing BPDUs and all incoming BPDUs on that specific port.
Wait, it just stops sending and listening for BPDUs on that port entirely?
Correct. It effectively disables STP on that single interface.
Why on earth would you ever want to do that on a switch-to-switch link? Isn't that just begging for a loop?
It sounds incredibly dangerous, and it is if used improperly, but it has very specific niche use cases. The most common is when you need to connect to entirely separate administrative domains or networks that share a single layer 2 link, but they absolutely must keep their internal STP topologies completely separate and unaware of each other.
Like connecting your company network to a partner's network over a direct fiber link.
Exactly. Maybe you have just one link between you and you don't want their BPDUs potentially destabilizing your root bridge election or vice versa. By enabling BPDU filter on that single interconnecting port on both sides, you prevent any STP interaction between the two domains.
But what's the catch? The massive risk.
The massive risk is that you are now relying entirely on the physical topology to prevent loops between those two domains. With BPDU filter enabled on that interface, if someone accidentally plugs in a second cable between your network and the partner network,
STP can't detect it.
STP is completely blind to it on those filtered ports. You instantly have a catastrophic, undetectable layer 2 loop spanning both domains. Game over.
So, using interface-level BPDU filter requires absolute certainty that there is, and always will be, only one physical path between the filtered interfaces.
Absolute physical assurance. It's a tool used with extreme caution in very specific scenarios.
Okay, very clear on the risks there. Moving on, sometimes the threat isn't an accidental connection or a rogue device, but maybe a legitimate switch in your network that's misconfigured, or maybe a switch in a less trusted area trying to take over the network.
Right. Protecting the root of your network is paramount. That's where root guard comes in.
Root guard. The name implies its function.
Exactly. It's all about maintaining control over who can become the root bridge, or more specifically, where the root bridge cannot be located. You typically enable root guard on switch ports, often trunk links that connect towards other switches you don't fully control or trust, or just downstream switches that should never become the root.
So it acts like a gatekeeper on that port.
Precisely. It monitors the BPDUs coming in on that port. It prevents the election of any root switch whose path is through that root guard-enabled port.
What happens if a switch connected downstream, say, in another department or a partner network connected via that port, gets misconfigured with a super low priority, like 0, and sends a superior BPDU trying to claim it's the new root?
Root guard, configured on your switch's port facing that neighbor, intercepts that incoming superior BPDU. It says, nope, you are not allowed to become the root through this port.
And its action is?
It doesn't just block the BPDU, it puts the port into a special STP state, often called root inconsistent.
Root inconsistent. Does that block traffic?
Yes, effectively, the port stops forwarding traffic while it's in this state. It blocks the port to prevent the network from adopting this suboptimal or unauthorized root switch, thus protecting your intended topology and keeping your designated root in charge.
Does the port stay blocked forever?
No, that's a key difference from BPDU guard. Root guard is temporary. The port automatically recovers and transitions back to its normal STP state, like forwarding or blocking, depending on the BPDUs it then receives, as soon as those superior BPDUs stop arriving on that port.
So if the misconfigured downstream switch is fixed or powered off, the port comes back online automatically.
Correct. It protects the root position without requiring manual intervention to re-enable the port later.
Okay, that's a useful control mechanism. One last major feature to cover, loop guard. This one protects against something really insidious, right? The unidirectional link failure.
Yes. Loop guard tackles a very specific and dangerous failure mode that can trick standard STP-RSTP. It's primarily designed to prevent forwarding loops caused by unidirectional links.
Unidirectional, meaning traffic only flows one way. How does that happen?
It's most common with fiber optic links. You might have a pair of fibers, one for transmit, one for receive. One fiber might break or have a faulty transceiver, so traffic can successfully transmit out from switch A to switch B, but switch B's return transmissions back to switch A fail.
But the tricky part is, the link might still show up status.
Exactly. Because switch A can still send light signal, and maybe switch B can too, just not be received properly, the physical layer interfaces on both switches might remain in an up-up state. The operating system thinks the link is perfectly healthy.
But the communication is broken in one direction. How does that affect spanning tree?
It breaks the BPDU exchange. Let's focus on the switch that is normally subordinate on that link, the one whose port is typically a root port, RP, or an alternate port, ALT, because its neighbor has a better path to the root and is the designated port, DP.
Okay, the downstream switch.
Right. Due to the unidirectional failure, this downstream switch suddenly stops receiving the hello BPDUs from its upstream neighbor, DP.
The link looks up, so it doesn't immediately know the neighbor is gone.
Correct. It relies on its STP-RSTP timers. Since it's no longer receiving hellos confirming that its neighbor is the designated port for the segment.
It eventually times out the old information.
Yes. After maxage in STP, or missing enough hellos in RSTP, it concludes, my designated neighbor must be gone. Since the link itself still looks physically up, the subordinate switch incorrectly assumes that it must now be the only active switch on that segment responsible for forwarding.
So it tries to become the designated port itself.
Exactly. It transitions its own port, the former RP or ALT, into the designated port role, and following normal rules, moves it towards the forwarding state.
But the actual designated port on the other switch, the upstream one, never went down. It's still forwarding traffic towards the downstream switch because its transmit path works.
Precisely. Now you have both ends of the link thinking they are the designated port, and both are in a forwarding state. Traffic arriving at the upstream switch gets forwarded down, and traffic arriving at the downstream switch, maybe from somewhere else, now gets forwarded back up. You have an instant forwarding loop created entirely by the undetected unidirectional failure.
Wow, that's nasty. How does LoopGuard prevent this?
LoopGuard is typically enabled on non-designated ports, specifically root ports and alternate ports on switches that might be susceptible for AG, those further from the root. It keeps track of whether it's actually receiving BPDUs on these ports.
Okay.
If a port with LoopGuard enabled, which should be an RP or ALT, stops receiving BPDUs from its expected neighbor DP, but the physical link remains up,
LoopGuard steps in.
yes. LoopGuard prevents that port from making the mistake of transitioning into the designated port role and subsequently into the forwarding state. Instead, it moves the port into a special loop-inconsistent blocking state.
Another inconsistent state, like RootGuard. Does it block traffic?
Yes, it blocks traffic on that port. By preventing the subordinate port from incorrectly becoming a DP in forwarding, LoopGuard effectively breaks the potential loop caused by the unidirectional link condition.
And does it recover automatically if BPDUs start flowing again?
Yes. If the unidirectional condition clears up and the port starts receiving BPDUs again, LoopGuard will allow the port to return to its normal STP or STP state determination.
So LoopGuard is absolutely critical for environments using fiber optics where these unidirectional failures are more common.
Absolutely critical for robust fiber deployments, yes. It protects against a physical layer anomaly that the basic link status lights simply cannot detect, but which can have catastrophic consequences for layer 2 stability.
Okay. We have covered a massive amount of architectural ground today. Feels like we went from zero to expert pretty fast.
It's a dense topic, for sure.
We started with that foundational disaster scenario, the broadcast storms, the AMI-C table instability, the multiple frame transmissions that happens without any loop prevention.
The why behind it all.
Then we moved through the core mechanics of the spanning tree algorithm itself, defining the root switch based on the lowest BID, how non-roots find their single best root port based on cumulative cost, and how designated ports are elected on each link.
And stressing that influencing the bridge ID priority and the individual link costs isn't just tweaking, it's fundamental design work required for predictable, optimal network behavior.
Right. Then we trace that critical evolution. From the agonizingly slow convergence of traditional STP, remembering that 50-second wait dictated by MaxSiege, listening and learning.
Oof, yeah, the bad old days.
To the dramatically faster world of RSTP, achieving that sub-second speed by shifting from passive timers to active peer-to-peer message coordination, especially that proposal agreement handshake and the explicit use of the alternate port role for instant failover.
Huge leaps in performance and reliability there.
And finally, we dove into the practical operational toolkit, stressing why Ether channel is king for availability, understanding the crucial risk-reward calculation of port fast, and deploying the defensive capabilities of BPDU guard, root guard, and loop guard to protect topology and handle specific failure modes or misconfigurations.
Absolutely. The complexity we've unpacked today, all these rules and features, that's really the engine that provides the foundational stability that every single modern high-speed redundant network relies upon. You really have the full architectural blueprint now.
So what does this all mean for you listening? Hopefully you now have the knowledge not just to understand spanning tree, but to predict its behavior, to control your network topology actively, not just react when something breaks.
And maybe to appreciate the elegance hidden beneath that complexity, to leave you with a final thought to mull over, building on those operational tools.
Yeah.
Consider that critical trade-off we discussed between two of those safety net features, BPDU guard and the global form of BPDU filter used with port fast.
Right. Guard disables the port instantly. Filter disables port fast but keeps the port up, falling back to slow STP.
Exactly. Now imagine two different environments. First, a high-security banking network, where any unauthorized physical device connection is immediately highly suspect and potentially malicious. Second, maybe a large public library network, where users might accidentally plug things in frequently, causing inconvenience, but where brief standard STP convergence times might be slightly more tolerable than instantly killing a port someone needs.
Okay, high security versus public access.
In which scenario would you absolutely choose the swift, aggressive, zero-tolerance action of BPDU guard, even knowing it kills connectivity on that port? And why is that immediate sacrifice of connectivity potentially the correct, necessary design decision in that specific context? Think about the tolerance for downtime versus the tolerance or lack thereof for unauthorized or unexpected devices on the network edge.